In today's video lesson, we're going to introduce ourselves to solutions and learn how to calculate the concentrations of different types of solutions. So the question is, why do we use solutions in chemistry? Well, many substances used in labs are much easier to store and to use in solution form. So we may order our chemicals in crystal form, but to actually react them together, they need to be in aqueous solution. So we'll prepare solutions of those compounds. So like I said, many reactions only take place when the reactants are in solution. And remember, an aqueous solution is a solution where the solvent is water. And just a reminder of the different terms. So the solvent is the substance that's holding the solute. So the solute is the thing that's dissolving in the solvent. Solvent is usually the most abundant material, and then the solute would be in lower quantities. The solvents that we tend to use are aqueous, so water, but solvents can be many different things. Some solutes won't dissolve in polar substances, so they won't dissolve in water. So they would have to be dissolved in something else. So then the combination of the solute and the solvent is called the solution, which is what we'll work with. So you've probably heard of the terms concentrated and dilute. So concentration describes the amount of solute relative to the volume of solution. So generally, we will measure our solutions concentrations in moles per liter. But you can also measure them in parts per million, parts per billion, and even percent concentration. So a concentrated solution is a solution that has a high amount of solute in the solution, in the solvent. So it would have a high concentration. A dilute solution is a solution that has a low amount of solute, so not very much at all. So the way I think about concentrated versus dilute, if you think of frozen juice, they're concentrated. So there's a whole lot of juice particles and not a lot of water particles. To make the juice palatable and to the right concentration, we dilute it with several cans of the concentrate of the water. So that would be a comparison of concentrated versus dilute. So now we'll talk about solubility. And solubility is the amount of solute that can dissolve in a set volume of solute at a given temperature. And this will vary depending on the substance that you're trying to dissolve. Some substances will be insoluble in water. They won't dissolve at all. Others will be able to dissolve readily, and it all depends on their properties. So remember, ionic compounds and polar solutes are able to dissolve in water, and non-polar substances would not be able to. So an unsaturated solution is a solution that does not contain the maximum amount of solute, so more could dissolve. So that's generally what we would be using. We would not want to have more solute in the solution than can be held, because then you'll have solid solute resting at the bottom. So a saturated solution is a solution that contains the maximum amount of solute. So no more solute can dissolve. Any more you would add to the solution would just remain as solid solute, would not dissolve anymore. Now a supersaturated solution is a solution that can contain more solute than normally possible at that temperature. And the way you can do that is you heat up the solution and you can dilute extra solute at that higher temperature. And then it remains in solution even when it cools down, but it can actually very quickly be returned back. So we will do an example in class where we will create a supersaturated solution, but then we'll jostle the container, and then it will cause the solute to come back out and crystallize. If you've ever used those reusable hot pads in your mittens, they actually involve supersaturated solutions. So there's a little metal disc within. So you boil the hot pad, in water to make the supersaturated solution. And then when you want the heat to be released again, you click the little metal disc in your heating pad, and then everything will crystallize again and release that extra heat that you had placed in the solution, and then you'll have a nice warm hot pad. So there are several things that affect the rate of dissolving. First of all, temperature. So the higher the temperature, the faster a solid solute will dissolve. If you've ever tried to stir drink crystals into cold water, it often takes a long time to stir up. It would actually be easier to dissolve them when the water is hot and then cool your drink. The lower the temperature, the faster a gaseous solid will dissolve. So that's interesting. And then stirring or shaking will increase the rate of dissolving, and we've all experienced that. You could put drink crystals into your glass, but they're not going to dissolve very well unless you stir or shake your container. And then also crushing a solid solute will increase the rate of dissolving because it increases the surface area. And then the water particles can access more surfaces and increase the rate of dissolving. So if you had one giant crystal to dissolve in your solution, it's not going to dissolve very well because it has to the only places that it can dissolve are where the water can access. So it would have a very low surface area to volume ratio, so it would take a long time to dissolve. So solvents can be polar or nonpolar. So polar solvents will dissolve polar solutes. So ionic compounds, methanol, sugar molecules would all dissolve in a polar solvent. And an example of a polar solvent would be water. Water would easily dissolve sodium chloride or any of the materials listed above. Nonpolar solvents will dissolve nonpolar solutes. So, for example, iodine is nonpolar. It won't dissolve in water, but it will dissolve in kerosene, which is a fuel, which is also nonpolar. So parts per million and parts per billion are ways of expressing extremely dilute solutions of substances. If you remember, percent means out of 100. Parts per million or per million means out of a million. So how many parts are there in a million particles? And then another one would be parts per billion, means out of a billion. It usually describes the concentrations of something in water or soil or even air. And we'll go through some examples of how to calculate parts per million and parts per billion now. So to calculate parts per million, you would take the mass of the solute in grams, divide it by the mass of solution in grams, and multiply it by 1,000,000, or 10 to the power of 6. Parts per billion, same thing. You would do mass of solute divided by mass of solution, make sure that the masses are the same units, times 10 to the power of 9, or a billion. So our first example states that there are 0.01 grams of calcium fluoride in 20,000.0 grams of solution. Express this in parts per million. So we would set up our equation. So remember, parts per million is equal to the mass of the solute over the mass of the solution times 1,000,000. So we would put 0.010 grams in 20,000 grams times 1,000,000. And make sure you do a quick check to make sure the units match. So they're both in grams and not milligrams. If that's the case, if the units don't match, you'll have to convert one to match. And once you perform that calculation, you'll see that there's 0.50 parts per million. So our parts per million is still quite small. So half of a calcium fluoride per million. So in our next example, we're being told that there's 2.5 milligrams of sodium chloride and a 2.1 kilogram trout. Express this in parts per million. And then it says, hint, the mass of the trout is equal to the mass of the solution. So we want to find out how much sodium chloride is in the trout. But you'll notice that we have milligrams and kilograms. So we need to convert to an equal unit. So if we convert to grams, so there's 1,000 milligrams in every gram. So we'll need to divide that by 1,000. So 2.5 divided by 1,000. You can move the decimal place over 3 as well. So 0.0025 grams. And then there's 1,000 grams in a kilogram. So we need to multiply that one by 1,000 or move the decimal place over 3 to the other direction. So that's 2,100 grams. Now we can perform our calculation. So parts per million is equal to the mass of the solute, so 0.0025 grams in 2,100 grams times a million. And that is equal to 1.19. We have to round off to two significant figures, so that would be 1.2 parts per million. So now we'll talk about molar concentration. This is the one that we will normally discuss. So molar concentration is the amount of solute in moles per volume of solution. So this will allow us to do stoichiometry calculations. So much more meaningful way of discussing concentration. Now remember, it's in liters or decimeters cubed. So this value is what you'll be seeing on IB assessments, decimeters cubed, whereas in Canada we usually use liters instead. And you'll notice that this is another triangle where moles is at the top this time instead of the bottom. So I'll show you a way of combining the twin peaks that we learned about before to include this triangle as well. So we like to call it, or I like to call it, triple peaks. So if we take a look here, this was our original twin peaks where the mole was the central part, and it still remains the central part. The mole is the thing that we're focused on when we're talking about stoichiometric relationships. So now we've added our third triangle at the bottom, which is why I call it triple peaks. So 1, 2, 3 peaks. We can now convert between number of particles, find the number of moles, and then find the mass. Or you could do number of particles to find the moles to find the concentration in a volume. Or you could do mass to find the moles to find the concentration. Or if you need to know the volume of this that you need to add to make this concentration. So we can work interchangeably amongst these triangles. So in this example, we've been given the following. So 200 milligrams of lithium chloride is dissolved in 80 milliliters of solution. What is the molar concentration of lithium chloride in moles per liter? So first we'll list what we've been given. So we've been given the volume is equal to 80 milliliters, but that's not in liters. So we're going to divide by 1,000 to convert to liters or move the decimal place over 3. So that's equal to 0.0800 liters. And then we've been given the mass of solute, or the massium lithium chloride. So that's equal to 200 milligrams, which is equal to 0.2000 grams. We also can find the molar mass. So the molar mass of lithium chloride is equal to I'll just erase that. Is equal to 6.94 plus 35.45. That is equal to 42.39 grams per mole. So now we can find the molar concentration. So remember, to find the number of moles, that's equal to the mass over the molar mass. So that's equal to 0.2000 grams divided by the 42.39 grams per mole, which is equal to 0.004718 moles. Now that we have that, we can find out the concentration. So C equals N over V, and that's equal to our 0.004718 moles over 0.0800 liters. So that is equivalent to 0.590. Sorry, 0.0590 moles per liter. So as you can see, if you're given the mass of solute and the volume, you'll have to do a two-step process. So first find the moles and then find the concentration. And you can do that using triple peaks.